Hello everyone, welcome back to Deeksha Karnataka YouTube channel, and today in the top 30 of KCET 2025 exam we are going to discuss two chapters combined, semiconductor and dual nature of radiation and matter. So it will be a combined two chapters at one go. Now you have to remember that in the semiconductor chapter a lot of portions are deleted, so if you are preparing for any other competitive exam, those portions may not be deleted. For that, for example, in JEE mains and in NEET exam, logic gate is still there, but in case of KCET, logic gate portion is completely deleted, general diode is completely deleted, so you don't need to worry about those questions which are based on logic gates, truth table, etc. Okay, so those are deleted. Whatever you have studied in your PU board, the same thing is there in KCET exam as well, but the question level may be little difficult. Some mixed concept questions also might come from the chapter semiconductor, and in case of dual nature as well, I think there is nothing deleted, but dual nature is a very easy chapter. Both chapters combined 7 to 8 questions you can expect. Okay, 7 to 8 questions. So this is a very serious and important session for all of you. If you have missed some of the previous videos, it's okay, but this video you cannot miss. Okay, you have to share this video with all of your friends so that everyone can get those 7-8 marks in the KCET exam. Right, now let's start with the first chapter, that is semiconductors. Let's check the first question, and questions are not super difficult as you are thinking that okay, whatever the question might be difficult, some questions will be difficult, but overall out of 7-8 questions that you are going to get, 5 to 6 questions will be easy, 1 to 2 questions will be difficult. Let's see. When a PN junction diode is forward biased, which type of charge carrier flows in the connecting wire? Now connecting wire is made up of conductors, and in conductors only electrons can flow, nothing else can flow, so only free electrons can flow in a conducting wire. So answer will be option D, free electrons. Next question. A full wave rectifier with diodes D1 and D2 is used to rectify 50 Hz alternating voltage. The diode D1 conducts dash number of times in 1 second. So in one wave, this is one wave. Okay, 50 Hz frequency means this type of wave is basically passing every second 50 times. Okay, 50 times this wave is passing through the circuit. Now D1 conducts in this range and D2 conducts in this range. So out of this, every 50 times in a second there will be a diode will conduct, diode D1 will conduct 50 times, diode D2 will conduct another 50 times. Okay, so total number of conduction is 100, but diode D1 will conduct 50 times only, so it will be 50 times only. Next, in fact in the half wave rectifier also the diode conducts 50 times only, because there is only one diode, the second half no diode conducts. So if the same question was asked in case of half wave rectifier, again the diode will be conducting 50 times only. The energy gap of an LED is 2.4 eV. When the LED is switched on, the momentum of the emitted photon. So this is a question which is linked with dual nature of radiation and matter. From this chapter we might see some questions which is actually linked to dual nature of radiation and matter. Only the LED part is from semiconductor, other than that everything else is from dual nature of radiation and matter. So the energy gap is 2.4 EV. So if you want an excited electron comes from the excited band to the valence band, from conduction band to valence band, you will get that 0.24 EV energy out of the diode, right? So what is the energy? Formula for energy is H nu by H nu. H nu is equal to 2.4 EV. Now what is EV? EV to joule, how to convert? To convert it into joules you have to use 1.6 into 10 to the power of minus 19. Now this is the energy. Okay, and they asked you what is the momentum of the particle, right? Now to calculate momentum, first of all you have to remember that you can calculate using de Broglie principle. So lambda equals to H by P. Okay, lambda equals to H by P, or what is lambda? Lambda is equal to So C equals to nu lambda, or lambda equals to C by nu, right? So you have to put that value over here. So it will be C by nu equals to H into P, or momentum P will be equals to H nu by divided by C. Okay, H nu divided by C, very very important. So what is H nu? H nu is the energy which we have already calculated. Now we have to put that value over here and calculate the momentum. That's it. Okay, so basically this formula is from Einstein's equation and this formula is from the Broglie equation. So you have to put them together. 2.4 into 1.6 into 10 to the power of minus 19 divided by C is 3 into 10 to the power of 8, right? So 3 8s are 24, 0.8 will be here. Now it will be 16 into 8. So what you can do is you can multiply it with 8 and then you can add one decimal. So it will be 6 8s are 48 and 4 8 12. So it will be 1.28 into 10 to the power of minus 27, minus 19, and there is a division of 10 to the power of 8, so it will go up and it will become 10 to the power of minus 27. So answer is 1.28 into 10 to the power of minus 27. Not this one, sorry, this one. Okay, 1.28 into 10 to the power of minus 27. Unit is kg meter per second. Next question. Okay, so here we have launched Abhyas KCET test series. So if you are someone who is preparing for KCET 2025 exam and still you want to practice more and more questions with expert guidance, also with the solution for each and every question, so definitely Abhyas KCET test series is for you. If you have not yet purchased, already 1000, more than 1000 students already registered and using Abhyas KCET test series. The link for this is given in the description. You can go there and you can join the League of Toppers today. Okay, also if you score less than 1000 rank, there is a cash reward for you. I am not going to discuss about the reward in this video, but there is also a cash reward if you score below 1000 rank. Now here you have to remember that you are getting total 35 tests, okay, 4 part tests and 31 full syllabus, full length tests, okay, across subject. You will get detailed video solutions, you will get chapter wise one shot revision videos, you will get chapter wise insight for last 5 years of KCET exam. And also we have launched Comet K crash course. This is a crash course, fully online crash course. Here you will get 4 mock tests. Out of the 4 mock tests, 4 part tests and 8 full length tests will be there. Complete syllabus coverage in for 11th and 12th. You will get 5-year previous year questions for each and every chapter. Live doubt solving sessions. So we will be coming live and we will be discussing any doubts that you might have. Class notes and recorded videos, everything will get in recorded format and class notes as well. So whenever you have some doubt on anything, you can come live and you can ask us. We will be going live and we will be asking you whatever questions you have. It's a fully online crash course along with tests and teaching material. The price for this is only 1999. This Comet K exam is for not only for Karnataka, this is also for students outside Karnataka, only for private colleges across Karnataka. Now let's move on. The resistivity of a semiconductor at room temperature is in between. So the resistivity, very very important, resistivity of a semiconductor, not the conductivity. Okay, resistivity is very very high for insulator, resistivity is very very low for conductor. For semiconductor it is between some range. Also here the unit is given in centimeter, okay, ohm centimeter, so it is not in ohm meter. So whatever, if you have studied some values in ohm meter, the exact value you have to convert it into ohm meter so that you get the exact value. Okay, now this is an insulator because its resistivity is very very high. Okay, and if you see, this is a conductor, its resistivity is very very low. Okay, this is also an insulator. Its resistivity is very high as well. This one is, by the way, falls between conductor and insulator. So this is the resistivity for a semiconductor. If you convert this into meters, it will be 10 to the power of minus 5 to 10 to the power of 6 ohm meter, which is the resistivity of a semiconductor. Okay, this is the resistivity of a semiconductor. This is the exact range that you are looking for. So this is the resistivity. You have to remember that all the higher values are insulators, all the lower values are conductors. Okay, this is in terms of resistivity. If the same question was asked in terms of conductivity, okay, for conductivity you have to remember that for semiconductor it is 10 to the power of 5 to 10 to the power of minus 6 in terms of conductivity. Okay, resistivity, high resistivity means low conductivity. Okay, low resistivity means high conductivity. This is resistivity, this is conductivity. Okay, now next, the forbidden energy gap for germanium crystal at 0 Kelvin is, the forbidden energy gap for germanium crystal at 0 Kelvin is 0.71 eV. Okay, next, identify the incorrect statement. These are very tricky questions. So basically 3 of them are correct, 1 is incorrect. So you have to find the incorrect statement. When a PN junction diode is forward biased, the width of the depletion region decreases. Yes, width of the depletion region, as you are increasing the forward biasing voltage, the depletion region slowly decreases. So this is the correct statement. Okay, when PN junction diode is reverse biased, the barrier potential increases. Same thing, opposite. Okay, so if you do forward bias, depletion region decreases. If you do a reverse bias, barrier potential increases, which is actually same thing. So this is also correct statement. A photodiode is operated in the reverse bias, and LED is lightly doped PN junction diode which emits spontaneous radiation of forward biasing. So photodiode operates in the reverse bias. Correct. This is also correct, but I think this question, exact same question will not come, because these 2 portions are now no longer part of your syllabus. These 2 portions are, but these 2 are not. Next, 3 photodiodes D1, D2 and D3 are made up of semiconductors having band gaps of 2.5 eV, 2 eV and 3 eV respectively. Which one will be able to detect light of wavelength 600 nanometer? Now again, this is a question which is based on dual nature of radiation of light. Only the photodiode parts are given. The question language will be changed because photodiode directly is not part of the syllabus, but same question might come in your exam as a different language, that there is a detector which can measure, which have a energy gap of 2.5 eV, 2 eV and 3 eV. Which of them can measure or detect the wavelength 600 nanometer? So you have to find the energy associated with 600 nanometer, and then you have to be sure which one can measure. So what is the energy of the 600 nanometer? If it is falling greater than any value, the diode will not be able to measure it. If it is less than or in between any 2 values, then that diode can measure it. Let's see. So what is the energy associated with this? Energy associated is h nu, right? That is h c by lambda. Right, lambda is given in nanometers. Now you have to remember that there is a fixed value of Hc, which is basically 1240, okay, eV nanometers. Okay, so this is the unit of Hc. When you convert it, you can use the joule value, then it will be very huge mess. Okay, but we don't want to do that. We want to solve it quickly. So only what value you have to use? You have to use the 600 value over here. Okay, and we can cancel the zeros. There is a nanometer obviously here, 600 nanometers, right? So nanometer will cancel, so only eV will be left. So basically this is a way to get the answer in eV. Now for our understanding, what we will do, instead of 1240, we will assume this to be 1260. Why? Because we want to cancel this number. So 6 tens are 60, 6 twos are 12, 6 ones are 6. Okay, so it is basically slightly less than 2.1, but it is still greater than 2 eV. So it is 2.1 eV. So anything more than 2.1 eV band gap can measure this. Okay, anything less than that will not be able to measure it. Okay, so definitely 2 eV, that is D2, will not be able to measure it. D1 can measure it because it is 2.5 eV, and D3 can measure it, it is 3 eV. So D1 and D3 can measure it, but D2 cannot measure it. So D1 and D3 can measure it. So whenever you are detecting a wavelength or detecting a light, okay, the band gap should be more than that of the wavelength of the light, or energy of the light. Okay, then only it can detect. If it is less than that, it will not be able to detect. Next question. A 220 volt AC supply is connected between points A and B as shown in the figure. What will be the potential difference V across the capacitor? So let's see. Here we have a 220 volt AC, right? Now if there is only one diode is here. Okay, only one diode is here. Now if you assume that the diode is ideal, so no drop is happening across the diode, so what will be the output? So this is a only single phase diode, only one diode is there, so it will be like this. Okay, so the maximum value, so the what the capacitor will do, capacitor will charge up to this point. Okay, then it will start discharging, and then again it will charging again. Okay, so this is the function of the so if you see that this 220 volt is basically the RMS voltage. 220 volt is the basically the RMS voltage, and across the capacitor you will get very close to that RMS voltage only. You will not get the, so there was slight mistake in this. The actual value of the capacitor will be equals to that of the maximum peak value, which is equals to 220 root 2 volt. Okay, so answer is option B. So when the maximum value that of the potential that is across the capacitor C is basically the maximum peak voltage. Peak voltage is 220 into root 2 volt. Here 220 volt AC means it is obviously it is the AC RMS value. So the peak value will be root 2 times the RMS value, which is 220 root 2. Now let's move on to the next question. In N types of semiconductor, electrons are majority charge carriers, but it does not show any negative charge. The reason is, so why does a N type semiconductor remains neutral, or why does a P type semiconductor remains neutral? The reason behind is that it is consisting of atoms of semiconducting elements, right? So and some external impurity. Both are in atomic form, and atoms normally are electrically neutral unless and until you are considering ions. Okay, they are not ions, they are normal atoms. You are using normal atoms, so this basically atoms are electrically neutral. So option C is correct answer for this question. Now next, question number 10. A positive hole in a semiconductor is absence of free electrons, an artificially created particle, an antiparticle of electron, a vacancy created when an electron leaves a covalent bond. It is basically not absence of free electrons, it is a vacancy created by an electron when it leaves a covalent bond. Very, very important. Okay, so you see absence of free electrons, you mark it. Actually it is wrong. Next question. The density of electron hole pair in a pure germanium is 3 into 10 to the power 16 meter to the power minus 3. At room temperature, on doping with aluminium, the hole density increases to 4.5 into 10 to the power of 22 meter to the power minus 2. The electron density in doped germanium will be. This is a similar question that came in your PU exam as well, and this is from one of the previous year KCET exam. My bet is that in your final KCET exam there will be a question based on this concept. So this is a very, very, very important concept. So if you have not studied this kind of questions, you have to study it. Also after solving this, you can open your PU final question paper and answer that question as well. Now let's see what is the question is about. So here we know that intrinsic semiconductor has some concentration, okay, carrier concentration, that is generally represented by mu I. Now when you dope with something, okay, it gets the hole concentration and the electron concentration now gets separated. Okay, now mu I square is equals to mu E into mu H. Mu is the electron concentration and mu H is hole concentration. Now in an intrinsic semiconductor, mu E is equals to mu H and that is equals to mu I. So this formula holds perfectly true. In fact, in case of any other doped material also, the same formula holds true. So let's put the values over here. Mu I is 3 into 10 to the power of 16. So 3 into 10 to the power of 16 whole square equals to mu E, electron concentration we are trying to find. The whole concentration is given 4.5 into 10 to the power of 22. So 4.5 into 10 to the power of 22. Okay, so what is the electron concentration? It will be 3 square is 9 and 10 to the power of 16 square is 32. Divided by 4.5 into 10 to the power of 22. So as you see that values are very good, they will cancel each other and you will get 2 into 10 to the power of 10. Okay, 32 minus 22, 10 to the power of 10. So answer is 2 into 10 to the power of 10. Right? Now next question. In the figure shown, if the diode is forward voltage dropped, if the diode forward voltage drop is 0.2 volt, the voltage difference between A and B. So you can see that this is also a different kind of question which might come in your exam because as I said, Zener diode is out of syllabus, so this kind of question is very favorite. So here you see that there is a resistance of 5 kilo ohm, there is a current passing through this, that is 0.2 milliampere. Okay, there is another resistance over here, it is also 5 kilo ohm, and because current is passing through the circuit, that means the diode is definitely forward biased, no doubt about it. Okay, here we have a filter, definitely it does not allow any direct current to pass through it, only alternating current can be passed through it. So it basically it is called, that's why it is called a filter. It blocks all DC current, it gets saturated and all DC current does not pass. So you can basically ignore this part, it is not at all required over here. Only thing you have to consider this thing. Okay, what is the voltage drop across these points? That will give you the total voltage drop. Okay, so 2 milliampere is current, 5 kilo ohm is the resistance over here. So what is the voltage drop across this? Resistance into current. Now milliampere and kilo, milli and kilo, they are basically reciprocal of each other. Milli is 10 to the power of minus 3, kilo is 10 to the power of plus 3. So they will cancel each other. So basically what we will do, we will simply multiply 5 into 0.2 and that will give us the value in volt. Okay, so this is 0.2 into 5, which is basically 1 volt. Okay, and 0.2 into 5, this is equals to another 1 volt. So total VA and VB, the voltage should be 1 plus 1, that is 2 volt. But it is also mentioned that there is a drop of 0.2 volt across the diode. So 0.2 volt is across the diode as well. So what is the total voltage drop? Voltage is always add. So basically 1 plus 1 plus 0.2, it will be 2.2 volt. Okay, the value will be 2.2 volt. Okay, not 1.8 volt or not 2 volt only. Okay, so basically you have to apply the Kirchhoff's voltage law. Okay, V into I plus this direct voltage, which is 0.2 volt, that will give you the total voltage drop across these 2 points. Okay, got it? Next question. The energy gap in case of which of the following is less than 3 electron volt but greater than 0? Okay, so less than 3 electron volt and greater than 0, that means it's a semiconductor. If it is equals to 0, it's a conductor. If it is a Greater than 3 electron volt, it's a insulator. So here we have to find less than 3 electron volt. Which one of them is semiconductor? Only germanium is a semiconductor, so answer would be germanium. Aluminium conductor, iron conductor, diamond is insulator, so it has a higher than 3 electron volt. So basically germanium is the correct answer. Now let's move on to EM waves. As I said, the semiconductor does not have too many questions. Many questions are deleted, so if I add any more questions, either it will be too much repetitive or you will feel that the question is very easy. So that's why we have added not EM waves, sorry, it will be dual nature of radiation and matter. So what I can do, I can erase this and I can say it is basically dual nature of radiation and matter. Okay, now let's see the first question. In an experiment to study photoelectric effect, the observed variation of stopping potential with the frequency of the incident radiation is as shown in the figure. So this is the graph, okay, stopping potential, frequency of incident radiation, and this is stopping potential. Okay, the slope of y-intercept is slope and y-intercept. This is the slope tan theta, and y-intercept is basically this one. What is the value of this? So for that we have to remember what is the equation. So equation was, if the stopping potential was V, so EV, okay, E is charge of an electron into V, is basically equals to h nu minus h nu naught, right? That was the formula. Okay, stopping potential into charge of an electron is basically h nu minus h nu naught. So from there we can find that stopping potential equals to h by E into nu minus h nu naught by E. Right? So what is the, first we have to find what is the equation, this, what does this equation represents. So what is the stopping potential? Stopping potential is along the y-axis, so we can write y equals to mx plus c. This is the equation, right? Intercept form, in the intercept form, straight line, equation of straight line. This is a straight line, right? Now what is y? Y here is v, y here is v. Okay, what is m? M is the slope. And what is x over here? X is frequency nu. Frequency nu is the x. So that m should be the slope, which is basically h by E. Right? And what is the intercept c? Intercept c will be the entire thing. Now intercept c generally comes with the plus form. Here as you can see, it is coming with the negative form. So h nu naught by E is the intercept. So h nu naught by E is intercept, and this is the slope. So option D is correct answer for this question. Now next, a 60 watt source emits monochromatic light of wavelength 662.5 nanometer. The number of photons emitted per second is. So what is the energy of the source? Energy of the source is 60 watt per second, 60 joules per second basically. So we are basically, because we are doing it per second, so 60 watt becomes 60 joules. If you have multiply with 1 second, you get 60 joules. So energy is 60 joules. One wavelength of one light is 662.5 nanometer. So what is the number of photons? How to calculate it? 60 equals to, say, total number of photons, say small n. Okay, and energy of one photon is h nu. Energy of one photon is h nu. So we can write this as n into h c by lambda. Right, hc by lambda. This is from here we can calculate the number of thing. Now here remember that I told you hc has a value in EV nanometer, but here the source is not given in EV, so you have to use the real value of h, no other option in this given case. But I will just simplify it little bit so that I don't get confused. So n equals to 60 lambda divided by h into c. Now you have to put the values, nothing else you can do here. Okay, so 60 into 662.5 nanometer. Nanometer means 10 to the power of minus 9. Okay, divided by H. H is 6.625 into 10 to the power of minus 34 into C is 3 into 10 to the power of 8. Okay, so now this will be cancelled and here you get 100. So values are given such that most of them will be cancelled. Only thing that you need to calculate is about the 10 to the power value. Okay, so you can guess either A or C is the answer because it is not coming any 5 over here. So 20 into, let's see what is the 10 to the power value. 10 so 10 to the power of there is 2 here, 2 minus 9 over here. Okay, minus 34 goes up, becomes plus 34, plus 8 goes up and becomes minus 8. So what is the value over here? There is also one more 0 over here. We will take care of that after we find the value here. So it will be 36 minus 17. 36, okay, 2 plus 34 is 36 and minus 9 minus 8 is 17. So it will be minus 17. So it will be 19. Okay, so it will be 20 or 2 into 10 to the power of 20. Okay, so it was coming out to be 10 to the power of 19. If we take that 0 as well, then it becomes 10 to the power of 20. So 2 into 10 to the power of 20 is the correct answer for this question. Now next question. In photoelectric experiment, if both the intensity and frequency of the incident light are doubled, then the saturation photoelectric current is doubled. Saturation photoelectric current is doubled only because saturation photoelectric current depends only on the intensity. It is independent on the frequency. So saturation current will be doubled because it is directly proportional to the intensity of light. Now, next question, the kinetic energy of the photoelectrons increased by 0.52 eV when the wavelength of the incident light is changed from 500 nanometer to another wavelength which is approximately. Okay, so first of all here the change in energy is given. Change in energy is given and suppose initially the kinetic energy, say Ek, same formula, Ek was h nu 1 minus h nu 0. Okay, now this was first case. Second case, suppose another you changed it to 500 nanometer to some other value and you get this to be h nu 2 minus h nu naught. This is phi, this is constant. So what is the change in the energy? Ek. Change in the energy is basically h nu 1 minus nu 2 and this value is given 0.52. Now again it is given in terms of wavelength. So what I will be doing, I will be converting it into wavelength. Hc by lambda 1 minus hc by lambda 2 equals to 0.52. Now here we will use our old weapon. What is that weapon I was talking about? I am talking about Hc. Hc is 1240 eV per nanometer, eV into nanometer. So if the value is given in nanometers, we don't need to worry too much about. So we can simply put the values in nanometers. You don't need to convert anything into meters. Okay, that is the beauty of this value. Okay, if you are using this conversion, you don't need to think about, okay, it is given in, we have to convert it into meters. No. So this value includes the nanometer conversion factor as well. Okay, so let's see what is the value. 1 by 500 minus 1 by lambda 2 equals to 0.52 divided by 1240. Okay, or so you can say this is basically, or 1 by lambda 2 equals to 1 by 500 minus, it will come to this, that side, this will go to the other side, it will be 1 by 2400 approximately, or 2500 say. Okay, it is almost double of that. 0.52 means half, so it will be almost 2500. Okay, so that I can do the LCM easily. Okay, so it will be 2500 and this will be 5 and this will be 1, so it will be 4 by 2500, or lambda 2 equals to 2500 divided by 4, which is equals to 25 into 25, which is 625 nanometers. So answer will be very close to 625 nanometer, and from the given answer the closest value is 700 nanometer. So answer will be 700 nanometer. Okay, how did I calculate this? 2500 means 25 into 100 divided by 4, so it will be 25. So 25 into 25 is 625. From there I calculated. I have approximated the value, so it will be slightly more than that, which will be 700. I have approximated, I have increased in the denominator, so it will be slightly more than whatever we have calculated. So correct answer will be 700 nanometer. Next question. The de Broglie wavelength of a particle of kinetic energy K is lambda. The wavelength of the particle, if it is kinetic energy, is K by 4 is. So what is the kinetic energy formula? Kinetic energy we already know, Ek is equal to hc by lambda, okay, minus h nu naught. Okay, so kinetic energy is given by K. So this value of Ek is K for a wavelength lambda. Okay, so for a wavelength lambda, this is K. Now for another value, the kinetic energy is K by 4, and for that, what is the value of this lambda? We are trying to find that, say lambda 1, and that will be minus h naught here as well. Okay, so we will be trying to find that out. Let's do the subtraction over here. If you do the subtraction, we get K minus K by 4 equals to hc by lambda minus hc by lambda 1, or it will be 3K by 4 into equals to hc is common, 1 by lambda minus 1 by lambda 1. Let's solve it in a different way. So K is basically hc by lambda minus that constant phi. Okay, the wave function, right, or work function. Now from here we can say that K is basically proportional to 1 by lambda. This is a constant, so we can ignore that, and we can say that kinetic energy is directly inversely proportional to lambda. So if you change it to K by 4, then the lambda must be equals to 1 by 4 lambda. Right, so the wavelength will be 4 lambda only, so it will be 4 lambda. Okay, so basically what you have done, you have divided 4 here, you have multiplied 4 here, so directly K by 4 means the wavelength will be 4 lambda, inversely proportional, that will be the relation. So if kinetic energy decreases, lambda increases, as simple as that. The work function of a metal is 1 electron volt. Light of wavelength 3000 angstrom is incident on this metal surface. The velocity of the photoelectron is. So work function is given, wavelength is given, and you have to calculate the velocity of the emitted photoelectrons. Okay, now this is slightly tricky. I am not going to solve it. This kind of questions I have not seen in latest part. This was one of the older question of the KCET exam. So what is the formula? Formula is kinetic energy is basically hc by lambda minus phi naught. Okay, now hc is basically 1240 divided by 3000 angstrom means 300 nanometers. Okay, as I said, this formula is valid for nanometers only, so you have to convert it into nanometers, and then you can do 10 3 4s are 12, 3 4s are 12, and then 3 1s are 3, 41. Okay, so it will be 4.1, approximately 4.1 minus 1 eV. Phi naught is given 1 eV minus 1, so it will be 3.1 eV. Now you have calculated eV. Now Ek is half m V square. Okay, that is equals to 3.1 into 1.6 into 10 to the power of minus 19. That is why I am saying I am not going to solve it. You have to put the value of mass of the electrons as well. Okay, I don't remember the exact value, 10 to the power of minus 27. So exact value you have 9 point some value, right? So that value you have to put over here, and then you have to cancel whatever you can cancel, and then you have to find the square root of that to find the exact velocity. It is a very tricky long question. Okay, not super easy. Anyway, what we can calculate is what is the 10 to the power value from there, closest 10 to the power value. If there are not super close, then we can find it. So it will be 10 to the power of minus 19 minus 27. It will be 10 to the power of minus 8, right? Minus 8. Square root of V, this is basically 10 to the power of 10 to the plus 8, sorry, minus 27 plus 19, so it will go up, it will become plus, so it will 10 to the plus 8, so it will be close to 10 to the power of 4. So from the 10 to the power of 4 calculation, I can see this should be the correct answer. Okay, as this should give you one value, and then there is no numerator and denominator, there is not super difference. Okay, so you will get 10 to the power of 4. So from there I can guess the answer this. Okay, so this is also another way to guess your answers. Now a proton moving with the momentum p1 has a kinetic energy 1/8 of its rest mass energy. Another light photon having energy equal to the kinetic energy of the photon possesses a momentum p2. Then the ratio of p1 minus p2 by p1 is equal to. So proton moving with the momentum p1 has kinetic energy 1/8 of its rest mass energy. So what is the rest mass energy? Rest mass energy is mc square. Okay, now if the momentum is known, what is the relationship between momentum and kinetic energy? So momentum is basically square root of 2m(e)k, right? This is the formula. Okay, now momentum is given p1. What is kinetic energy then? So kinetic energy will be ek will be p1 square by 2m, p1 square by 2m, and this is basically given as this value. Kinetic energy is 1/8 of 2m, 1/8 of the rest mass energy, right? So you can cancel this, it will be 4. So p1 square is basically m square c square by 4. So p1 equals to mc by 2. So p1 equals to mc by 2. Similarly, we have to calculate p2, and then we have to calculate this value as well. Okay, another light photon having energy equals to the kinetic energy of the photon possesses a momentum p2. Okay, now next is a photon which having the same energy as the kinetic energy. So its total energy is equals to kinetic energy. Okay, total energy is kinetic energy, and it possesses a momentum p2. Now what is the energy of a photon? Energy of a photon is basically equals to, now rest mass of photon is 0, so you cannot use this equation for photon. So for photon, lambda equals to h by p, okay, or p equals to h by now this photon has the same energy as the proton. So what is the energy of the proton? Energy of the proton is 1/8 of the rest mass. So what we have to do? We have to put the value of, this is P2. So P2 will be equals to 1 by C into 1/8 of its rest mass, that is mc square. Okay, so one of the C will cancel, so you will get mc by 8. So one of them is mc by 2, one of them is mc by 8. Now we have to find the relation P1 minus P2 by P1. which is equals to MC by 2 minus MC by 8 divided by MC by 2. Okay, so it will be 1 minus, so you can cancel this and you get 1, and this one will cancel with this and you will get 1 by 4. So it will be 3 by 4. So answer will be 3 by 4. You can simplify it and you will get the answer. Okay, I have solved it quickly. So because these of them are equal, so basically what is the meaning of that? P1 minus P2 by P1 can be written as 1 minus P2 by P1. Right, that formula I have used over here, and we got it as 3 by 4. So option D is correct. Now next question. This is a very interesting question. The last question was very, very interesting. Okay, even it took some time for me to solve as well. Light of two different frequencies whose photons have energies 1 eV and 2.5 eV respectively successively illuminate a metallic surface whose work function is 0.5 eV. Ratio of maximum speeds of the emitted electrons will be. Now here what is the formula? So half m V1 square equals to energy minus work function, 1 minus 0.5. Don't waste too much time, directly apply the formula. M V2 square, which is equals to 0.5. Now you leave it here only. M V2 square is energy of the photon, and this is the work function, equals to 2. Okay, now you have to find the ratio of the maximum speed of the emitted electrons. So first one is 1 eV, second one is 2.5 eV. So that same order you have to find. Now what we will be doing, we will just divide this. Okay, so we will get V1 square by V2 square, right? Half m will cancel, right? So what we will get? We will get 0.5 by 2, which is equals to 1 by 4. Right, so V1 by V2 is square root of that is equals to 2. So the ratio is 1 is to 2. So 1 is to 2 is the answer for the question. Next, this is a very common question from one of your previous year KCET exam. The following graph represents the variation of photocurrent with anode potential for a metal surface. Here I1, I2 and I3 represents intensities, and nu1, nu2 and nu3 represent the frequency of the curves 1, 2 and 3 respectively. Then let's see what are all the relationship. So here we have three graphs, 1, 2 and 3. As you see that these two have the same stopping potential. These two have the same stopping potential means the frequency are same. So nu1 must be equals to nu2. Same stopping potential means frequency is same, and nu2 and nu3 are different. Now these two, 3 and 2, have the same saturation current. So intensity of 3 must be equal to intensity of 2. So these two are the correct relationship. Anything else is not correct. Let's see if we have any of the correct. First is intensity wise, frequency wise, nu1 equals to nu2 is given in two options, in this and in this. Now in this case they have given I1 equals to I2, so this is not correct. I1 is not equals to I2, but in this case they have given I1 not equals to I2, so definitely this is the correct. I3 is equals to I2 and I1 is not equal to I2, so option C is correct answer for this question. Light of certain frequency and intensity incident on a photosensitive material causes photoelectric effect. If both the frequency and the intensity are doubled, the photoelectric saturation current becomes doubled. So option D. Next question. The number of photons falling per second on a completely darkened plate to produce a force of 6.62 into 10 to the power of minus 5 Newton is N. If the wavelength of the light falling is 5 into 10 to the power of minus 7 meter, then N is equals to. How to solve it? So it is basically talking about force per second. Only the saving part is the 1 second part. So how to do that? So basically you have to go back to your second law and you have to remember that force is basically rate of change of momentum. Okay, so what you have to calculate is from the wavelength of light you have to calculate the momentum of light. Okay, so wavelength is h by p, or momentum is basically h divided by lambda. Okay, what is h? H is given here 6.62 into 10 to the power of minus 34. And what is the wavelength? Wavelength is given here is 5 into 10 to the power of minus 7. This is the momentum, right? Now, so here we will get, it will be 5 ones are 5, 3 5s are 15, 5 2s are 10. So it will be approximately 1.32. Right, into 10 to the power of minus 27. So this is the momentum of the photon. Right, now already it is told that this much change in momentum is happening every second. This much momentum carried by the photon hitting the surface coming to a rest. So change in momentum is basically this. This is the same amount of change in momentum, and this is happening per second. So we can say that this is the change in momentum for one photon. Okay, suppose n number of photon is falling, then n into 1.32 into 10 to the power of minus 27, this should be the total amount of force acting on the object, and that force is basically given by 6.62 into 10 to the power of minus 5. Right, so n is basically equals to 6.62 into 10 to the power of minus 5, and minus 27 is in division, it will go up and it will become 10 to the power of 22. Total will be 10 to the power of 22 divided by 1.32, so it will be 5, because here we cancelled with 5, so we got 1.32. now here we are doing the opposite, so the answer will be 5 into 10 to the power of 22. So 5 into 10 to the power of 22, so answer is 5. So here 10 to the power 22 already given, so 5 should be the answer here. Now next question, the maximum kinetic energy of emitted photoelectron depends on, maximum kinetic energy depends only on the frequency of the radiation, and saturation current depends on the intensity. Next, a proton and the alpha particle are accelerated through a same exponential difference v. The ratio of their de Broglie wavelength is. So if they are accelerated through same potential difference v, okay, what is the energy gained by the proton? Energy gained by the proton is basically E into V. Charge of a proton is E, okay, a positive E, we are only considering the magnitude. So for proton energy gained is EK equals to EV, and what is the corresponding momentum? Corresponding momentum will be square root of 2 MeV. Right, so what is the corresponding wavelength? Corresponding wavelength will be h divided by p, which is equals to h divided by square root of 2 MeV. Okay, now we can directly use this formula for helium as well. Only thing you have to remember that what is the charge of helium or alpha particle. Alpha particle is basically +2 of helium, right? So the charge will be for helium or alpha particle, this is for proton. So for alpha particle, charge is basically 2e. So the same formula, we only need to use the charge 2e, potential difference is v. Now what is the mass? Mass of helium is, mass of alpha particle is 4, right? It has 2 protons, 2 neutrons, so it will be 4m. Right, now you have to calculate what is the value over here. Okay, so it will be h divided by 4 will be coming out 2, and we will get another 2 over here, but here we will get mv, right? mve. So this is the wavelength of the helium particle, alpha particle. So now we have to find the ratio of the proton and the alpha particle. So what is the proton? Proton divided by alpha particle. Proton is this value, H divided by root 2 MeV, and alpha particle is H divided by 4 square root of MeV. So H cancels, this will go up, this is division, right? So 4 MeV divided by square root 2 root MEV cancel, so you get 2 root 2. So answer will be 2 root 2. Okay, 4 by root 2 is 2 root 2. Now next question. An electron is moving with an initial velocity v equals to v naught I cap, and in a uniform magnetic field B is equal to B dot J. Then its de Broglie wavelength decreases with time, remains constant, increases and decreases periodically, increases with time. Let's see. So V and J are in the same direction, are not in the same direction, they are in the perpendicular direction. So in the perpendicular direction means the particle will rotate with the constant velocity in a circle. Okay, a particle will rotate with a constant velocity in a circle, right? That is the condition. Lorentz force. So this is also a mixed concept question. So now Lorentz force means the force acting on the particle will act in towards the center. Okay, it will not accelerate in the anything other than this direction, right? And the velocity will remain constant. So velocity, magnitude of the velocity will remain constant. That means the magnitude of the momentum will remain constant. So magnitude of the momentum constant means the de Broglie wavelength will remain constant. Okay, de Broglie wavelength will remain constant. A particle is dropped from a height h. The de Broglie wavelength of the particle just before reaching the ground depends on the height as h to the power minus half, h to the power 0, h to the power plus half. Let's see. So what is the formula? So first we have to calculate the velocity and then momentum. So if you drop it from on some height, okay, just before touching the ground, what is the relationship? What is the velocity? Suppose the velocity is v. At this point the energy was mg h, and at this point the energy is half mv square. So half mv square equals to mg h. Okay, or you can calculate the velocity. Okay, v is equal to square root of 2g h. So what is the momentum? Momentum is mv, which is nothing but m into square root of 2g h. So what is the de Broglie wavelength? De Broglie wavelength is h by p, which is equals to h divided by m square root of 2gh, right? Or you can say this is directly proportional to h to the power minus half, right? Division, square root means half, division means minus half, so it will be minus half. So answer will be b h to the power minus half. Next question. From the following graph of photocurrent against collector plate potential for two different intensities of light I1 and I2. So these are the two different potential, I2 and this is I1. Okay, what you can guess from this diagram, I1 and this is I2. Right, obviously we can see that both of them has same frequency is same, and intensity I2 is greater than I1. These are the two things that we can see from the graph. Let's see. So I2 is greater than I1, option C is correct. Okay, it has a higher saturation current. Higher saturation current means higher intensity. So obviously they have not given you direct answer, they have given you indirectly, so that you have to know that this one, whoever gives this is bigger, so whoever has this opening towards them is bigger, whoever receives this R's is smaller, right? If you remember this. Now question number 17. The variation of photocurrent with collector plate potential for different frequencies of incident radiation nu1, nu2 and nu3 is as shown in the graph. Now here it is exactly the opposite of the previous question. So frequencies are different, nu1, nu2 and nu3. Okay, so obviously you can see that nu3 has the highest cutoff, so nu3 will be biggest value. So nu3 greater than nu2 greater than nu1. Okay, whoever has the highest cutoff potential or stopping potential, that will have the highest frequency. So definitely again similar trick is given over here, nu1 less than nu2 less than nu3. Okay, now the de Broglie wavelength of an electron accelerated to a potential 400 V is, so what is the energy of the electron when it is accelerated to a potential of 400 V? Okay, so energy associated with the electron you can calculate to be kinetic energy of the electron accelerated to 400 V is 400 into charge of an electron, that is 1.6 into 10 to the power of minus 19. Okay, or for simplification what we will do it 4 into 10 to the power of 4 into 16. So I have removed this decimal and I have taken 1 0 borrowing from here, so now this becomes 10 to the power of minus 18. Okay, so I have just rearranged it, 1 0 I have taken from here multiplied with this, so it becomes 16, another 0, the remaining 0 I have multiplied over here and it becomes 10 to the power of minus 18. So this is the kinetic energy. What will be the momentum? What is the relation? So momentum is basically square root of 2m into Ek. Now here I guess the mass of electrons should have been provided in the problem. Otherwise what I will do, I will just use 9 into 10 to the power of minus 31 into 4 into 16 into 10 to the power of minus 18. So it will be 3 into 10 to the 4 is 2 into 4 into 10 to the power of 2 into 10 to the power of minus 49. Okay, so this is the I have to do a little bit more approximation. We will do it in a while, but first let's see this one. 3 to the 6, 24. Okay, I will do the approximation about this in a while. First, what we have to do, we have to find what is the formula for wavelength. Formula for wavelength is h divided by momentum. So h is 6.6 into 10 to the power of minus 34 divided by the division value is 24 into, now let us take one of the zeros from there, and what we will do, we will make it 20 into 10 to the power of minus 50. What I have done, I have taken I have multiplied 1 0 over here and I have taken this 2 outside. So it will become 6.6 by 24 into this 20. I am for now considering this to be 25, which is really big number, but anyway this is the easiest way to solve it without using calculators. Okay, so I am just using it and it becomes 10 to the power of minus 25. Order of the answer will be same, right? So that is our target. So 6.6 divided by it will be, let's do the math, not 100, less than 100. No, sorry, it will be closer to 100. 25 into 5 is 125, 24 into 5 is approximately 120, but I will consider this, okay, let's consider 120 only, that will be easier. 10 to the power of minus 9. Okay, minus 34 divided by minus 25, so it is the minus 9. So nanometer we have received, so it will be 0.2, right? If I divide by 6, no, 1.2, sorry, 6 ones are 6, 6 ones are 6, 6 ones are 6, 6 twos are 20. Now it will be 0.5, 0.55 by 10. So the answer will be 0.055 into 10 to the power of minus 9 meters, or 0.55 nanometer. So answer will be 0.06 nanometer. Okay, so the nearest answer is 0.06 nanometer. Okay, even though we have done the approximation, we have reduced the value. Remember, by increasing the denominator, we have reduced the value. So the answer will be higher than whatever value we have calculated, right? So answer will be 0.6 nanometer. Okay, now with this I like to conclude this lecture. The questions were very interesting, especially for dual nature of radiation and matter chapter. A lot of different types of questions we have solved today, and if you want to solve more such questions, don't forget to join me on this Saturday 12 AM in the morning. I will be live with a lot of different style of questions that you can solve live with me, so don't miss out on that. I will be back with the score booster series. In that I will be seeing you in live. Okay, so till then, bye. And I will be obviously there will be another class tomorrow morning for top 30 session as well, but Saturday morning I will be live with the score booster series, different taste of different style of questions. So I will be seeing you live there. Okay, bye.